Welcome to Intro to Surface Area. So the idea here is we are now going to study the surface area of a solid formed by rotating a curve about an axis. So we are going to focus on the X and Y axis. So focusing on the X and Y axis, let's just go ahead and split into our two cases. So we will have on the left rotating about the X axis. And then we will come back and look at rotating about the Y axis. So essentially, let's go ahead and start off with rotating about the X axis. So we start off with some curve, which we will then rotate about the X axis. Just like we would have done with our regions. That's just here, we're just rotating the one curve. And then this time around, we are studying that surface area, just the outside of the solid that we create. So the general idea for how we go about finding this surface area, we will focus on little slivers of surface area, which are essentially bands that go all the way around, sort of at one X value or at a little interval of X values. So we will focus on bands of surface area. And so what we will do is we will essentially take the little secant line and sweep it around. So this will be a little teeny secant line of over an interval of width delta X. Which is then rotated about the X axis. We'll come to the rule in just a little bit. So before we get there, our band, our little secant line that we're rotating, the secant line itself, oops, sorry about that. Okay. The secant line itself has length square root delta X squared plus delta Y squared, which we previously saw is equivalent to the square root of 1 plus delta Y over delta X squared, and then multiply by delta X outside the square root. We will then multiply that length by the circumference. Right? So then multiply that length by the circumference of the band. So for the band, our radius in this case is essentially f of x at some representative x value. So the radius of our band will be f of x for some x in our interval, or f of xi, or an xi in the interval. And so the circumference is 2 pi times that f of xi. So putting these together, we have that our band surface area is 2 pi times f of xi times the square root of 1 plus delta y over delta x squared times delta x. Then as we let those delta x go to 0, so as delta x approaches 0, then we get that this is equal to 2 pi times f of x times the square root of 1 plus f prime of x squared times dx. So this should look similar to what we did for arc length. We just have this extra 2 pi times the radius out front. So adding all the bands together, then we get the integral from a to b of 2 pi times f of x times the square root of 1 plus f prime of x squared dx. So we will now mirror this with y. So mirroring this with rotating about the y-axis. So in this case, to rotate about the y-axis, again, we're just focusing on the outside of the shape. Sorry, I'm just drawing a rotational solid about the y-axis. So in this case, again, we will focus on bands. So we will focus on bands which are just secant lines swept around the y-axis. So which are mini secant lines rotated around the y-axis. Again, the secant line will have length given by the same formula we've worked with before. So the secant line has length the square root of delta x squared plus delta y squared, otherwise known as the square root of 1 plus delta y over delta x squared times delta x. Again, we will multiply by the circumference. Of the band. So in order to do that, we need to know the radius. In this case, the radius is just the x value. So the radius will just be xi. For an xi in the interval. Which means that we have that the circumference is equal to 2 pi times xi. So for our band surface area, we get almost the same formula as for rotation about the x-axis, but this time it's an xi instead of f of xi. So we have this surface area is 2 pi times xi times the square root of 1 plus delta y over delta x squared times delta x. Again, as we let delta x go to 0, sorry for the scrolling. So as delta x goes to 0, we get that this is equal to 2 pi x times the square root of 1 plus f prime of x squared dx. So once again, adding all the bands together, we are looking at the definite interval from a to b of 2 pi x times the square root of 1 plus f prime of x squared dx. So in summary, for curve y equals f of x on AB, where f is continuous and differentiable, on AB, the surface area formed by rotating the curve first up about the x-axis is given by surface area is equal to, I'm going to pull the 2 pi out front. So 2 pi times the definite interval from a to b of f of x times the square root of 1 plus f prime of x squared dx. And rotating the curve about the y-axis, the surface area is given by surface area is equal to 2 pi times the definite integral from a to b of x times the square root of 1 plus f prime of x squared dx. So ultimately, we can just jump to these two formulas when we go to solve for the surface area of the rotational solid formed by rotating a curve about either the x or y axis. In the next video, we will go ahead and look an example at a couple surface area problems.